you can see from the data table that the trend in boiling points in the halogens is that it increases as you go down the group, and you probably knew that already. But here it just asks you to explain that. So, as always in melting boiling point questions, you need to start by talking about what kind of structure you have. So you need to say that halogens have a simple molecular structure, because remember they all exist just as diatomic molecules, F2, Cl2, Br2, etc. So simple molecular structure, and the importance of that is that it means that when they boil, you don't have to break the covalent bonds, they remain intact. So the intermolecular forces break when they boil. And then you need to specify what kind of intermolecular forces. That's almost always going to be too vague unless there's really no way you can know, but here you can, because obviously if we're talking about things like F2 and Cl2 and so on, they can't have hydrogen bonds because they don't have any hydrogen. They can't have permanent dipole-dipole forces because obviously the molecules are symmetrical, so there is no permanent dipole. So you need to specify that these are induced dipole-dipole forces. Those are the only ones that you can have with these kind of non-polar molecules. So these are induced dipole-dipole forces, and that's important because knowing the type of force tells you what factors control their strength. And the important thing here is that these get stronger down the group because the number of electrons per molecule increases. So in a fluorine molecule, each fluorine has 9 electrons, because that's its atomic number, so there are 18 electrons in a fluorine molecule. But chlorine has atomic number 17, so there are 34 electrons, so a lot more electrons per molecule, and that gives you stronger induced dipole-dipole forces. So they get stronger down the group as the number of electrons per molecule increases. The other factor that we've learnt about which affects induced dipole-dipole forces, remember, is the surface area for contact with other molecules. But you don't really use that one when you're comparing similarly shaped molecules. Obviously, you know, all these molecules look basically the same, they're just getting a little bit bigger. But the surface area thing comes in when you're comparing things like making a chain longer, or making it branched compared to linear, so when there's a change in the actual shape of the molecule. But here there isn't, it's just really the same thing, I guess, changing in scale a little bit, but the key factor then is the number of electrons per molecule. So if you talk about the surface area as well, it won't get marked wrong, but it will get ignored, and if you put that as the only reason, it won't get you the mark. So these get stronger down the group as the number of electrons per molecule increases, and always it's not enough just to talk about the strength of the bonds, you've got to relate that to energy. So that means more energy is needed to overcome these forces or to break them down. So the boiling point increases. Okay, so that's a sort of classic example of a boiling point question. So always the same strategy. What kind of structure is it? What does that mean about the kind of bonds you have to break? And what are the factors that control the strength of those bonds? And you just got to set it out clearly, and then the marks are in the bag. Part B wants the tests that will confirm you have NH4 plus and Br minus in ammonium bromide. It's not a well-worded question, it's not really clear from the question, but it doesn't expect you to do the whole thing of, you know, which you need to learn more generally, which is that, you know, first you test for carbonate, if it's not carbonate you test for sulfate, if it's not sulfate then you do the halide tests. Obviously you could put that in, but that wasn't expected. Here they just wanted the test that confirms NH4+ and the test that confirms Br-. I think it's a badly worded question, so make sure, don't ignore the fact that you need to learn that specific sequence, because in other questions you will need to know that. So the NH4+ test, remember what you do is you warm with aqueous sodium hydroxide. Okay, so it's important you specify aqueous sodium hydroxide, not just solid. And you test the vapour. Okay, so it's not the solution that you're interested in, because the solution obviously is going to be alkaline because you've added sodium hydroxide to it. It's the vapour that's produced, and you test it with either universal indicator paper or red litmus paper. Either one is fine. And that should be damp, because you're going to test for an alkaline gas in the vapour, but that will only react with the colour sensitive molecules in the paper if it goes into solution. So you need to have damp indicator paper, and the paper will turn blue if NH4+ was present. Okay, so that's the test. And the reaction for that is that NH4+ reacts with OH-, and when you heat it up, that gives you ammonia gas and water. And ammonia gas, of course, is the alkaline gas that's having that effect. So then the bromide test. As I say, we're skipping the preliminary tests to rule out carbonate and sulfate. I'm going straight for the halide test, which is that we add silver nitrate solution. Again, make it clear it's a solution. Okay, not just add silver nitrate, but add aqueous silver nitrate. And remember, what happens then is you get a precipitate with halide ions. It's white if it's chloride, cream if it's bromide, yellow if it's iodide. So you say a cream precipitate forms if Br- is present. You could add in the confirmatory tests about solubility in aqueous ammonia, but don't bother with that unless it's clear that it wants it, because so long as the colour's clear, that's definitive. It's just when the colour's not very clear that you need the confirmatory test. So wait to be prompted before you put that in. So the cream precipitate tells you it's bromide, and the equation for that is that the aqueous silver ions meet the aqueous bromide ions, and they just stick together to form solid silver bromide, and that's your equation.